Okay, so if you look on the boards around the room, everyone has the same correct answer. If we look at our balanced equation, we have 0 moles of gas on the right and 1 mole of gas on the left. So delta N sub G is 1 minus 0 is 1. Delta E is delta H minus delta N sub G times RT. So we plug in our delta H. We put in our delta N sub G as 1 mole, changing the units on R from joules to kilojoules per mole Kelvin, and multiplying by the temperature. We have the same nRT here, the absolute value, when we multiply this together. Because this is 571, we have to stop in the ones place for sig figs. So calculator says 568.521, but we report 569. So I think these are pretty straightforward. The key here is to remember the equation. So again, just write that relationship between energy and enthalpy down. And if you write that down someplace and you study and remember it, you should be fine with these, because the math is very straightforward algebra, not even any fancy stuff with logarithms. The biggest problem I usually see is that students will slip a sign, because they'll slip that negative or subtracting a negative number. So that was kind of a quick review, putting a new relationship into things we had talked about in Chem 111. Now we're going to introduce something that we didn't talk about in Chem 111, and this is the idea of spontaneity and the idea of entropy. When we talk about spontaneity, we say that something is a spontaneous change. It happens immediately by itself without outside assistance. And when we have a chemical reaction and the energy or the enthalpy is exothermic, where heat is given off, then those things tend to be spontaneous. However, that really isn't a true indicator of spontaneity. Because there are things that have a positive enthalpy that actually take energy or take heat energy to run the equation, but they still proceed spontaneously. And that's because there is another factor that predicts the spontaneity, and that is the addition of consideration of entropy. Entropy is kind of hard to define, I think. They say in chemistry books it's the measure of randomness in the system, or the number of equivalent ways the energy can be distributed. And I never found that very clear. So I think of it as entropy, more of the randomness and the chaos that exists in a system. And you've seen examples of this in your life. In everyday life, we see entropy changes all the time. If I were to just take this stack of cards and just take them and drop them on the floor, how many of you think that they would land nice and ordered like this on the floor? Nobody thinks that, because you know from your life experience, they'll just go flying everywhere, right? If I trip and drop them, there's going to be some at the back of the room that slide on the floor. So there's going to be more chaos. I think of entropy as chaos, and it's the randomness. So it is Mother Nature's way is to constantly increase the entropy in the universe. It's constantly increasing. And when we try and decrease the entropy, that takes energy, or it takes work. And I know that I think about chemistry a lot. I think about chemistry pretty much every day, every hour. Maybe for a few minutes I stop. But I even think about it in my everyday life. And it's part of the language I speak. And I can remember one very funny incident that happened as a mom. As a mom, I used to holler at my kids when they were making a mess. I had 3 children. We had a family room that had a closet full of all the kid junk. And so they were allowed to go in there and rummage through. And we would be after dinner, during relaxing time before baths, brushing teeth and going to bed. They could go in and do whatever they want. And then I would go in the room and say to them, okay, it's time to start picking your toys up and get your teeth brushed and go to bed. And sometimes I was foolish enough to leave the room thinking that they would continue to clean up and follow my instructions, but I learned after a while not to do that. So one day I was particularly aggravated with these children, and I had told them to, you've got 5 minutes more, you can go get your PJs on, brush your teeth, get ready for bed, clean up this room. And I came back and they had not done that, and I said, I want this room cleaned up now. And I left the room and I came back and they had not done that, and this doesn't go too well for me as a mom. And I actually stood there and said, if the entropy in this room is not reduced significantly within 1 minute, you are all going under house arrest for the rest of the week. So all of a sudden, my little darlings, they're jumping around, and they cleaned up the room. And so I would often tell them, go reduce the entropy in that family room. Well, the youngest is quite a bit younger than the others. And she was always picked on by her 7-year older brother, because that's what brothers do, right? It's their job is to irritate their siblings. So she was doing something. She had her crayons, or I don't know if it was crayons or markers, and she's coloring. And her brother went by, and just because he was her brother, and because he could, he just walked by the table where she was sitting and gave her box of markers, I think it was markers, a whack, so they just went flying all over the room. Now, she was about 3, maybe she was 4, and she looks at him and she stamps her foot and says, Adu, his name's Andrew, but she couldn't say it quite right, Adu, make entropy better. She wanted him to make the entropy better and clean up the mess he just made. He didn't, of course, until his mother came in and encouraged him to make the entropy better. So that's entropy. And you've known since a young child that things tend to get messier, right? You ever watch the Coyote cartoons, the Roadrunner, the Wile E. Coyote and the Roadrunner? So the coyote is always trying to catch the Roadrunner. And I love it. He goes to Acme for all his needs. So he gets an Acme rocket, and he straps on and he shoots it off and he goes flying off on this little rocket launcher to catch the Roadrunner, but he runs into the side of a stone mountain and he crashes in, makes a big hole. And then the next scene in the cartoon is he's sitting down on the ground and all of the little chunks of rock, they're all perfectly shaped like bricks, and they start going blip, 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 and they build up like a little cage or something around him. You've seen those things, right? And you laugh when you see that. Why are you laughing? Because that would never happen, right? You're laughing because that doesn't happen. And because it's funny because that is not nature. So even as a regular person not thinking about chemistry, watching cartoons, you know that reduction in entropy is not normal, right, in our universe. Okay, so we can think of this entropy and we use the letter S. I don't know where S came from. But it's a measure of randomness in the system. Maybe it comes out of randomness, the S, I don't know. But we call it S, so delta S is the final minus initial. For us in chemistry, the change in entropy, delta S, is equal to the entropy of the products minus the entropy of the reactants. If delta S is positive, then the reaction will tend to be spontaneous. Just like when delta H is negative, the reaction will tend to be spontaneous.